And I just, I'm making her.
Okay, we are very close to on schedule. I'm so excited about this. It's never happened before in something I've organized. So let's try to stick with it and get going on the next talk here, which is Hans Halvorson from Princeton University, who's going to tell us what models say.
Thanks, Jim. So I got the cursed afternoon slot where everyone wants to fall to sleep now. So, and I sadly don't have a joke. So, at least not one as good as Thomas's. So let me actually start with something that's maybe a little provocative just from a mathematical point of view. So what do models say? So, I'm going to hand you a model. Right? We're model centric. I'm going to hand you a model. It's that represents the world. So here's a model. What's the world like? So it's the empty set. Brackets just form singleton sets. So what's the world like? Well, the thing is it's totally ambiguous. Right? This could be various different worlds. This could be a world of three things. That could be the claim being made could be there are three things. Or the claim could be there are two things. And one of those two things has a property. Because the normal way we represent models is we have a domain of things. I could have written this in various different ways, but I want to keep it simple. Is we have a domain of things, so here's our two things, and then we have a set of subsets, a property. So the property is only had by this one thing. So it could be two things, and one has some property P. So the long and short of it is if I hand you a mathematical object, and this is the extreme of rigor. Anything less rigorous than this is in some sense less transparent. Although the problem is, for our intuitions, is we import familiarity into, we tend to think that familiarity is rigor. Right? This, of course, is what led to, in some sense, 19th century foundations of mathematics, is they realized, the joke goes that Euler's students were so bad, the followers of Euler were so bad at fixing themselves that they had to create the foundations of mathematics to fix that, right? Because Euler could do stuff, he could prove stuff reliably without reaching contradiction. His students tried the same stuff that he did and they kept contradicting themselves, so they had to invent foundations of mathematics. The point is, when we're familiar with mathematical objects, we tend to think they represent the world. If you strip away that familiarity, if you take away the words we use and you write it up in its bare sort of binary looking form, that doesn't represent a world until you put some words on it. So the first short answer is, what do models say? Absolutely nothing at all. Okay, but now I'll say something more hopefully helpful. Okay, so how do we use models? There's no doubt that contemporary physics uses mathematical models to represent physical reality. Let's make no mistake, we're not going back to the time of Newton where we talk about the world qualitatively. So it's true. In some sense, models will always dominate from now on, we suppose, certainly now, but from now on, our modeling, our representation of the physical world. However, there's another truism. And that's what we're going to have to cope with and try to make sense of here, is that physicists often can explain in words how they intend for their mathematical models to represent reality. Physicists don't just, if you could do such a thing, if it made sense to present a mathematical object in its purity, right, without ever speaking, right, of just handing it. Physicists don't do that, right? Even more so than mathematicians, right? Physicists explain how they intend for their mathematical models to represent reality. Okay, I'll say something a little provocative. When they cannot, they have a name. They're called instrumentalists. Okay, I'll back off and say two things. The first thing is, well, look, okay, there's a new game in town, as I'll say in just a moment, that I should be careful not to overstep my own pay grade, so to speak, is high energy physics today, the way it's going is different than stuff we've seen in the past, right? High energy physics, there's a reason why mathematical physicists kind of stay away from current high energy physics. They don't really know how to deal with it completely. There's an open question. Has the way we do high energy physics today changed the ballgame, so to speak? That is where we get to a stage of mathematical description where when we try to say how it represents the physical world, we're having trouble. That's a very, very big open question. Does high energy physics show that idea of discursive understanding no longer shouldn't be the goal of model building. I'll just say a disclaimer. If everything I say in this talk is sort of contrary to the direction physics is going, that's my own fault. I'm not qualified to speak about normal practice in physics. Insofar as I've hung out with physicists, I've hung out with a strange group of those who really are mathematicians. Okay, so, but forgetting for a moment the complexities of current high energy physics, if we go to sort of slightly more tame physics, let's start thinking about how models actually are used. And the first points I want to make, again, we're just talking about, is there a role for language here? And ultimately what I'm going to go for, again, the goal is understanding the use of models. First of all, we certainly go from language to model. As physicists and others use language to specify the relevant class of models. Of course, that goes without saying. Now, many people, when I've said these sort of things in the past, they say, okay, that's just a sort of accident, of our Constitution. Wouldn't it be great, if we could just produce it? More important to this discussion is the fact that they use language to identify the representationally relevant parts of the models. Again, that's the sort of thing where if I just handed this to you here and I said, lo and behold, the world, I need some words to tell you what I'm trying to communicate to you with that. Now, of course, as we'll talk about more shortly, is when I hand you a mathematical thing, I need that mathematical thing to have enough stuff so that I can represent the things I want to. So it has to have enough structure in some sense. But actually, this is the stronger point. That's not a thing so yes, that has structure, as any set theorist can tell you. But they're looking at it as a set theorist, which of course is not typically what we're doing in physics. I'll have lots of examples for you in a minute. It will start to become I don't have jokes, but I have a little bit of comedy coming. The comedy is, what if you try to do physics as a set theorist? It starts to get quite funny. So what we do use language in some interesting sense to identify the parts of our model we're wanting to use to represent reality. Now, here's the other way around too, though, from model to language. Physicists use models to make statements about the physical world. No, not surprising, not controversial, even in high energy, right? And that's where it's getting super fancy, because what you're doing is taking like mathematical models and you're taking limits and saying things about the world that you say are not fundamentally true and so on. But even in the tame cases, this is one of the beautiful things about mathematical physics, is you take a theory who maybe has very clear differential equations. What's not always clear, of course, is the solutions those equations will have. That's why it's fun doing mathematical physics. You get surprised that you come up with Einstein's field equations. Lo and behold, you have a model with closed time-like curves. That's fun. And so you can say things about what's possible that you couldn't have conceived of before, because you look inside the model and you extract linguistic description out of it. So it became very clear in the early days to the people who wanted to put models first, the semantic view of theories, they were very quick to not sound ridiculous, because it was pointed out, I myself didn't follow the early debate very closely, but I was given to understand that the first objection to the semantic view of theories was, dear Professor von Frazen, but models don't make statements. And of course, von Frazen had a nice, quick response. That's right. There was a hidden statement always, and one of the models represents. So the semantic view already said, to accept a theory includes you have this class of models, but you have to believe, or let's take it out of our heads and put it into language. You have to state that one of its models represents the intended object or system. So it has this dangling linguistic component. Now, the point I want to make in addition is, and I will make this claim boldly and then be happy to be refuted afterwards if it's called for. Model M represents reality is just not specific enough. It's easy to see that if you take trivial cases. 42 represents reality. It does actually, by the way, did you know that? It does. So, 42 does represent reality. That we see is a little bit silly, because out of context, that doesn't make any interesting statement. We start to get more confused when we go to familiar mathematical objects. If I say, now it would be really fun if I put R3 instead of just R. R3 represents reality. I go, oh yes, I know what Hans means. And I would go, no, actually you didn't, because I wasn't talking about space. I was talking about my dog, something like that. So the thing is, we tend to, with familiar examples, think we understand better maybe than we actually do. Okay, the last sort of clarification before I get into the more technical details here is there's a sort of, I don't want to make super strong statements about like there's sort of an evil kingdom, but nonetheless, there's a sort of it's very prevalent in contemporary philosophy. It actually motivates quite a bit of intellectual and technical work. And the sort of idea is, wouldn't it be great if we could take our models and we could rip away all of that stuff that we put in there by accident so that we have stuff that just represents the world. And I wonder sometimes at night, I'm like, why is this, what's the goal here? What's the real psychological issue going on here? And that's when I get really deep thoughts about this, some sort of like existential angst they have, is they're really afraid, right? They're really afraid that they're gonna have stuff in their models that doesn't match the world, and they're really afraid they won't be able to tell the difference, right? So physicists aren't normally bothered by this, right? Physicists, this surplus structure stuff, I've never heard a physicist go, oh my God, how do I get rid of the real numbers? The real numbers aren't in the world, but philosophers for some reason are very uptight about this. Philosophers want to rip the stuff off their models that's not in actual correspondence with reality. Here's a classic statement of it from Sider, who, thank him for stating things clearly at least. And this is actually comes in the context where he actually puts this almost in the third person. This is interesting, the paragraph that goes before this. He said, I think most metaphysicians believe something like the following, is what he says, ... It's fine to construct models with artifacts, but there must always be some way of describing the phenomenon in question that, in some sense, lacks artifacts. There must be some way of saying what is really going on. For example, although we can model mass with real numbers, there must be some underlying artifact-free description such as and this is the partial order and composition type representation of mass. This description, from which one can recover a specification of which numerical models are acceptable and a specification of which features of the models are artifacts. And I'm not in what follows going to argue against this. Actually, everything I say from here on is based on a rejection of this view. I'll come back at the very end to mention this again, but the fact is I don't feel it needs refuting. I mean, I could spend a long time telling you all the reasons why I think this is not just empirically false. This is literally misunderstands what it's like to be a human being. Literally misunderstands the nature of reality and the fact that there's contingency in reality. But nonetheless, what we want to do, because if this is not possible, we want to take a practice that is working just fine without us, right? A practice in physics of representing and very carefully and deftly knowing the difference between artifact and content. This is something one learns slowly and patiently in mathematics and physics practice. Philosophers would love to have it no longer need to be taught because we would just have an object that all you have to do is say it represents. That's not the case. So what we would like to do as reflectors upon the practice is try to understand what it is better. Why should we do that? I guess that's why we're in philosophy and not physics, is we're somehow wanting to understand how that works and not just do it. Okay, so here's where I'll go from here, is I'm gonna actually start in a little bit of a backwards way from my own normal practice, which is I'm really anxious to get on to. We have some fun formal things we could do, some things we could try to work on. I'm going to actually try to first say why it is a real issue by coming to three specific cases, by mentioning three specific cases. I'm going to talk first about quantum mechanics and representation of whatever's out there in the quantum world. In some sense, a very trivial example from a mathematical point of view. It will turn out actually it's I think the hardest example from just clarity of how you pick out what's the real content in the models. Then I'll talk about a totally mathematical example, surprise to come, and I'll talk a bit about relativity and relativistic spacetimes before I then go on to here's the formal work that might be done, which is actually more of a metamathematical nature. Okay, so the reason I want to talk about the wave function thing is I'm a spectator, a passive spectator to the recent discussions people have had about wave function realism. And my first passively spectating this discussion, I was like, boy, I've really missed how easy things are, right? To be a realist about quantum theory, especially if you're like me and you actually don't really care about measurements. You're like, maybe measurements don't have outcomes. I don't know. I've never done one, so. So measurement problems, who cares? But on the other hand, sitting in my office and if someone gives me the quantum formalism, I want to be a realist. I mean, come on, I'm not a bad person. So I want to believe it's true. So someone hands me the wave function and they're like, believe it. And I was, at first I was like, I don't know. But then I heard them say what I'm supposed to believe. And it's like, okay, that's great. There's a thing out there, the wave function, and it has properties. So this is from David Albert, his statement, and reporting GRW, Girardi, Rimini, Weber, on the GRW theory, or for that matter, and on any theory of collapse, the world will consist of exactly one physical object, the universal wave function. All that happens is that the function changes its shape in accord with the theory's dynamical laws. So here's the lowest price scientific realism about quantum theory. It sounds so wonderful, right? What's real? The wave function. Okay, that's good. I have an ontology. What properties does it have? Whatever properties, that real thing. So these guys aren't Platonists, right? The wave function is a representation of what's real. So what does the real thing have? What properties? Its shape. Awesome, right? So clear. Crystal clear. So which features of the wave function belong to its representational content and which features are representational artifacts? They've given me a very nice picture. I can see it, right? We're very familiar with waves, right? That's what it's like. That's its features. That's what I'm committing to, is there's a thing out there that's like that. It sounds really good until you actually get a little meta-mathematical or a little Quine-like and you start thinking about it. So the first thing I want to say is wave function realist. I'm going to be a little bit ridiculous just to point out, this is not a principle. That feeling of it having properties is not a principled notion of what properties it has and what it doesn't. So even they have to grant that some things of the wave function are just representational artifacts. So this is a little bit off. This first one, very quickly, the philosophers of language would get angry at me because they'd say, you've got to put things in quotation marks and so on and so forth. The wave function is written in computer modern font. It's an artifact. I say, no, it's not the wave function. It's your symbol for the wave function. Okay. The point was, whenever we put forward something, we have to make some choices about how to put it forward. They're like, well, there's something hidden behind your mark on your piece of paper. Okay, great. Tell me what it is. A set, right? What else would a wave function be? Oh, good. Now let the set theorists in and let them tell us what sets are like. So what is a wave function? It's a function. It's a subset of ordered pairs. Every subset of ordered pairs in the universe of sets is utterly specific, right? That is, it has elements in its domain. Every single element is a set. It has elements in its codomain. Every one of those is a set. Here's a predicate of set theory. So for a free variable S, the empty set is an element of U. So the wave function has properties. Here's one of them. The empty set singleton is in its domain. If this is really a mathematical object, now I'd be very happy if the conclusion of this talk is set theory is not the right foundations of math. And so we need a different foundation of math and that will fix these problems. That would be interesting, really interesting. But let's just be conservative for a moment here. The best story we have is this guy's a set. If that's true, one of its properties is which sets are elements of its domain. Give me a break. What physicist states that's the content that I'm telling you. When I tell you what the world is like, I'm telling you what elements are members. Okay, that's just to point out, this is one of the advantages about not actually knowing very much physics, is you can think of weird thoughts. Okay, so what are the real features of this thing, this wave function? Expectation values. We all tend to think that's true, right? That's the real stuff, it's the expectation values. this next thing, actually, I'm just going to skip because that's nitpicky in a way that it's not worth mentioning. And I already mentioned this one, pseudo features, what elements are of its subset. What elements are members of its domain. Now, here's where it gets kind of interesting because, look, we all agree, or at least, all of us who are not wave function instrumentalists, which I wouldn't say I am either. Look, that when I tell you the system, the quantum system is in a certain wave function, I'm trying to say something about the world. Even if I were somewhat operationalist and want to say something that's telling you about how things would turn out if I interacted with the system, I'm trying to tell you something about the world. So there's some things about the mathematical representation I give you that I believe in. What I don't believe in is the empty set or singleton of the empty set. So there's other stuff I do. Expectation values, we all sort of think, yes, it has statistical predicted features. Then there's other things actually that start to get much less clear, right? What about, so this guy is actually a function of the complex numbers. The exact value it takes at a point, is that part of my commitment when I think the wave function represents the world, that's the value it takes at that point? And there's lots of ways again that you can get mathematically nitpicky. One way is, let's not forget already actually that real wave functions are not actually functions at all. They're equivalence classes, modulo sets of Lebesgue measure 0. So actually the value of the wave function at a point is a non-well-defined notion. There is no such thing. Because for any wave function, you can replace its value at a point with any other value you want. They're mathematically equivalent. So that's actually, in that case, not even a real property. Now, I would be very happy then to back up and say, let's talk only about, for fun, let's talk about wave functions on countably infinite space where that issue is set aside. Well, then what about even in that next case about U1 gauge freedom, that sort of, I can multiply any wave function everywhere. First of all, global gauge freedom, I can multiply it everywhere by a complex number of unit length. Is that changing the state of affairs? Am I committed to the more the details of the actual value? So now what about the derivatives of the wave function? So expectation values tell you something, but what about the actual, even if you accept the value of the wave function at a point is something real, or whether you don't, do you take how much it moves up and down? These are all things that are not totally clear. So I'm going to leave that. I'll say a few words about the wave function again later, but that's just the point. It's much more difficult than you might assume usually. Again, practice is no problem. People doing real physics, except I've heard of corner cases. I heard recently actually of somebody accused another quantum information theorist who said, look, we have faster than speed of light transmission. And I heard the accusation was, actually, it's because you think this wave function has a property that's not really a property of the system. So there's something you thought in your representation was a piece of content that was just an artifact. Okay, so let's leave aside quantum for a while, this complicated case of the wave function. Let's talk about a purely mathematical example now. So this is no real interest in physical representation, but already the puzzles about what features your model has become relevant here. So here's group theory, elementary group theory, sets with a binary operation, certain properties. We all familiar with these kind of things. What are the real features? I hand you a group. We all have learned when we did group theory, right? This is one of the interesting things is you learn not to take too seriously some details of the group and to take very seriously other details. So we learn not to take seriously what particular elements are in the group. We learn to take very seriously things like, is the group commutative or not? So what do we think are the real features and what are not the real features? So among the real features, we certainly would say the cardinality of a group is real, right? That's not an artificial feature that it depends on how we represent that group. Whether it's abelian, commutative or non-abelian, we'd say it's real. If it's cyclic of order n, that's a real property. You can, the group's are isomorphic. So you start to get the picture before I go on here and make things a little more complicated. You say, Hans, you're making a mountain out of a molehill. It's just, you're talking about isomorphism and variance. Wait a minute and we'll see. That's neither a sufficient nor necessary answer. In some cases, it's not. So we know the pseudo features of G. G contains some particular element. And this, again, particular element, remember, if you're really thinking about sets, this is a set with an identity of its own. It's not just a label, right? This is a set. We think that's a pseudo feature, not in the sense that if I hand you a concrete group, you would think, that's a feature of the concrete group, but we do tend to think, I've been told otherwise recently, and this actually relates to the whole argument. I had forced someone into the dialectical position, which I thought was very disadvantageous, where they said, yes, when I hand you a space-time model, the actual sets that are the points of the manifold are important to me. And I thought, that's a checkmate. That's a consequence of the view I adopt. I tend to think, right, we would never think this is a feature, especially for physics representation, right? Physicists don't care what the elements are. Here's a more tricky case, because actually this guy is isomorphism invariant. Here's a feature of a group we don't think is, so a set theorist might like this feature, but a physicist doesn't care. It's equal to itself, and the continuum hypothesis is true. That's a feature the group either has or doesn't have, depending on the theory of sets. It's embedded. Okay, here I put this features of G liberalized. The original heading here was maybe, but the thing is, I don't want it to be trying to be too tricky. These really are features of G. It's just if you take a too naive view, you won't see it. G has n normal subgroups where some n is some fixed number. The reason that's a little bit tricky is that's not a first order property, right? That's not something that you can express in first order logic. And so is that a real property? I'm showing my colors here that I'm not a first order dogmatist, right? I don't think. So that's why that's interesting, is we tend to think that properties are real, even if you need higher order logic to describe them. Here's one that's interesting too, because G has, certainly physicists not only find this real, they find this of incredible importance. G has two irreducible representations. That tells you something, for example, the symmetry group, how many representations does it have? This is interesting from a metamathematical point of view because that's an extrinsic property, right? That's not something that is a feature of the inside of the group. Because saying it has irreducible representations is talking about mappings it has to other things that are actually not themselves groups. In this case, it's talking about representations on vector spaces. Nonetheless, nobody doubts that's a real feature of the group. Okay, so let's come back now to physics and talk about the third case, the case of spacetimes. And as I mentioned in the quantum case, that there actually are real physical examples of if you make the distinction, if you draw the distinction between content and artifact in the wrong way, you can make mistakes about the physics. This, of course, in some of our diagnoses is exactly what's at play in the whole argument, is what are features of a space-time model? Well, let's start in the middle with the real features. And thanks to the earlier talks from JB and Thomas, and they can say a lot more about this. Things like the scalar curvature has no upper bound, right? That's something that if a space-time has it, any isomorphic copy is going to have it as well. It's not going to go away. This is a real feature of the space-time model. A pseudo feature, well, take a particular point A, take the value at scalar curvature at that point. That's something that can be changed with under isomorphism, right? So you can move things around. We don't actually care about the identity of that point, so that's a pseudo feature. And possibly real features, which now related to the previous slide, I really want to call real features that might be a little bit surprising. Well, of course, a relativist will tell you this is, of course, a feature of a space-time or not, whether it's inextendable. However, that's not a feature. If you just stare inside the thing, you're not going to see that it's inextendable. You have to know where it sits in the ambient space. So the data we have at this point, before we move on to the next thing, is when you take a model, you want to know what properties there are. There's lots of stuff that you can say about a model, because the truth is any model, it's a concrete thing. As a concrete thing, it will usually have many features that physicists don't really care about in the representation. We'd like to say you can just look inside the model and you can see what's representationally relevant, but in fact, some of the representationally relevant stuff has to do with its relation to other things. So now we have a confusing mess of different data that we have to make sense of. Before I try to make sense of that, let me give a few other just general philosophical takeaway points here, discussion points. Do physicists sometimes take models with what I've been calling different features to be representationally equivalent? This really does depend on what you mean by different features, because again, I wanted to make sense of, or I want to make sense of this notion of a real feature of a model. Models, though, being concrete, they're going to have features that are more specific. So in this sense, if we take features in a liberal sense, so that sort of all the features it has as a set, physicists certainly would take things with different features to be representational equivalent. Here's the question driving the next bit. Is there a more refined sense of features, the real features, such that models are representationally equivalent only if they have the same features? And actually, if I could put this in a more flat-footed way, I mean, look, this makes it sound like a harder problem than it is, because I'm not actually really on to the deep question of representational equivalence. Like, who knows what that really means? I'm into this sort of very flat-footed inquiry of what is our normal practice when we look at models, what properties do we think they have and what properties do we not think they have? Downstream from that, we can talk about representational equivalence, but there's an easier question. What feature does the model have? So here's a few more things to throw into the mix. And these are all, interestingly, I've actually it's been very interesting to see the overlap between talks so far, given the fact that most of us didn't even know what the conference was about. This is really, really lucky, right? Roughly the same things. But so let me give you a few examples just to generate, to think about for what comes next. So thank goodness for the people already mentioned about Morita equivalence, which is a fascinating notion. Morita equivalence is both extremely liberal in a certain sense that makes metaphysicians very angry, and it's actually much more conservative than physicists normally take equivalence to be. So it's a very weird situation to be interested in this, because there's like nobody who's happy with it except Thomas and me. So here's the basic situation. Forget about syntax for a minute. So if you have two theories that are Morita equivalent, and as Toby mentioned, right, that's basically when the two models, they can define, or the two theories, they can define everything the other has, but they have a pretty flexible they have a lot of definable power in the sense of building new domains. Now, on the semantic level, if you go back down and you look at the models of two Morita equivalent theories, here's exactly what I can tell you is the models of one theory, every model of the one theory has a twin model called a Morita twin in the other theory. Now, how do these models compare to each other? And it's really pretty interesting because they don't have to have the same even number of domain elements in common. So you could have one of the models has 5 elements and one has 6 or something like that. But that doesn't mean it's the wild, wild west. It doesn't mean that, these have no interesting relation to it, because actually the relation between the two is tightly constrained. So it's roughly like this. These guys are Morita twins, every point in here is in a sort of Bertrand-Russell sense, a logical construction of things in here. Every single point here is a logical construction of things in here, and vice versa. And then any sentence that's true, any feature of collections of things will transport over to a feature of the logical sum of the collection of things, et cetera, et cetera. So there's all these nice construction procedures back and forth between the two. So in one sense, you might say, well, at first, it might look like if you say these two models of Morita twins, they don't have features in common. That's a very unflexible notion of having things in common, because they have a lot. So this is a tricky issue, because back to today's talk, they don't have structure in common in an obvious sense. It's not like I can take something here and find it here. It's actually much more like we experience with natural language translation. Right? So if somebody said to me, well, I'm only going to accept your translations of English into German if you can show the structure they have in common. And I would go, I'm in bad trouble now, right? Because they don't have many words in common, the two languages, right? So we normally don't require that of translating between two things, as they actually, there's some third thing that they share in common. So that's what we have here, is we have a very clear sense in some way of these have features in common, but they're not extractable from out of the models themselves. Okay. So here's the next example, which this is, I'll say, open formal problem. As Thomas showed some years ago, there's a very clear sense in which Hamiltonian Lagrangian mechanics are categorically equivalent. Physicists, of course, know that much more is true than that, right? It's not just that you have a category as this sort of cold collection of nodes called Hamiltonian mechanics, and this other category is cold collection of bare nodes called Lagrangian mechanics, and somehow this network can match onto this network. No. If you take a specific model of Hamiltonian mechanics, you can convert the bits, move them around, and get a model of Lagrangian mechanics. Right? So it's a stronger sense than categorical. So do those models have something in common? Now, I think we'll ask a real physicist to answer this question, but my sense as an outsider is they certainly do. It's a very clear sense in which they're describing the same situation. It's like you literally just change the words a little bit, right? So now, last case that, again, I didn't have time between our talks to just drop this in. It's just like a miracle. Maybe not a miracle. Dave and I have talked a bit over the years. So, but spacetimes and Einstein algebras. I also, again, tend myself to have my gut feeling is our words cause trouble because if we say their models have things in common, we tend to look for the thing that is in both, and that's not something we're going to have. But if we use different words and say, like, do they describe the same world? And then we start thinking, yeah, now I can sort of see it because what this calls a point, this calls a, limit of such and such, right? Okay, but these are open questions. So this is the sort of question is whether we have a sense of, we have models and sometimes the models don't prima facie look the same, could they nonetheless have the same content in some way? Okay, so I'm going to skip that part. Okay, so there's bad news and good news. And there's going to be an argument out of this. So I'm going to stick for now with the first order case because if that's problematic, then it's going to be even more problematic for harder cases. Even for a first order theory T, it's not totally clear what counts as a genuine feature of a model. And here's the argument. The argument is what you might call signature-free accounts are both going to fail, or they're all going to fail, but the two extreme cases, which I'll tell you about, will fail. So set theoretic accounts and category theoretic accounts. If you go to signature relative accounts, now this is potentially dangerous for some sort of math first view because this starts to sound like language. So signature relative means in the traditional logician sense, I'm using language to pick out the models. Here we have a sort of continuum of extremely conservative to extremely liberal. I won't say anything about this specifically because it's above my pay grade for sure. And I can't even pronounce his name. So, do you have a?
It's Varnanen.
Varnanen? Okay.
I misspelled it 4 times in the talk that I gave to him.
Yeah, so, okay, the Finnish guy. Okay, good. So let's start with the signature free. So here was the goal. And we just take a model, never mention, so like the thing I had on the board before, never mention what the signature is, never mention what the language is, and just try to say what features it has. And there is an old proposal that sounded really great, and I can make it laughable in 2 lines. So this is the old Patrick Suppes proposal. If phi is a predicate in the language of ZF set theory, such that ZF set theory proves the sentence phi applied to M, the model. Models are set theoretic structures, so just package it all together and call it a set. Then phi represents a property of M. Okay, no. Not if you want to be true to physics practice at all. And these are the examples we've already talked about, right? So physicists don't care about most of these. They don't care whether their model contains the empty set or the singleton of the empty set or the singleton of the singleton of the empty set. Physicists don't care about whether the continuum hypothesis is true for the most part. That can't be a model that can't be a property of the model that's very interesting to them, despite the fact that that's an isomorphism invariant property. And by the way, there's not many metaphysicians in the audience. I normally have to be careful of them. I'll add this for their sake. The problem is not this property here is extrinsic, because physicists do care about extrinsic properties, like the one before, how many representations a group has. So physicists, certainly when it comes to models, maybe they care about intrinsicness when it comes to physical objects, but models they don't. Okay, so let's just put aside the set theoretic thing, although I think there is something right about that in the sense that we tend to choose from the set theoretic properties those things we do think are genuine properties. A completely contrasting idea now, which you might think would be beloved, that I might love, but actually I recognize the limitations of for sure. It's going to appeal to category theory, but let's actually start with trying to make it sound like this is something a physicist would arrive at independently. So a model's relations, idea number one, a model's relation to other models is an important part of its important aspect of its use in physics. I already mentioned, the group, how many representations it has, in extendable spacetimes. Ignore that next bit; it's too detailed for now. So an important property of a model is not just. So if I give you a contrasting. Before, or one might have always thought, I tend to think, I don't know why it is, but philosophers, I think it's one reason the semantic view of theories it got bogged down in some trouble, is philosophers tend to, when they want to explain how things are, they tend to look at individuals and stare at them for a long, long, long time. And they look at another individual for a long, long, long time, and then they try to decide what relations they could possibly have to each other. So what we might be tempted to do is, if we want to know what features models have, is we might take individual models and stare inside them for a long time and say, that's what this is like. And it's my experience that physicists they maybe sometimes look at here, but they're often more concerned with how this is related to other things. So for example, like, is a space-time inextendable? So, I could stare at this all day long, but the question is there another space-time that's bigger that it can go into? And actually, I'm never going to figure that out by just staring inside this guy. So one thing you might say is, wait, let's actually totally turn this whole set theoretic thing on its head. Let's actually collapse these circles down to nodes that have no inside. And this is essentially the category theoretic mindset, is forget completely what M looks like on the inside, if that even makes any sense. M and other models, they sit in this network. And then you might think, I can't say anything about those. But that's not true. You can say tons of stuff about those. Okay, idea two, which plays into the same thing, is again, if you just look into, I don't know what made us think this in philosophical interpretation of physics, is we tend to think if I just stare inside here, I'll know what symmetries this has. But the category theoretic way of thinking about this is no, don't stare inside here, just look at what symmetries it has. Right? What arrows does it have to itself? And that's especially useful if you're actually trying not to get distracted by the sand that's inside your model. So like, let me give you a piece of advice, right, is if you want to do general relativity and understand what diffeomorphisms there are, don't stare at the points too much. Right? They look like they can be moved around a lot, and actually they can't be so much in a lot of cases. So model symmetries are a very important part of its use in physics. As Jim argued and disputed a little bit in the last talk, but actually in one sense, the way you understand what the inside of a model means to you is what you think about how that model relates to other models. So if you have a piece of stuff inside your model, but also in the back of your head, you're thinking, I can move that piece of stuff around and I get something equivalent, you don't really believe that piece of stuff is in the world, per se. So that's just the way you think. And that's actually very useful, especially if you don't have a quote unquote quotient representation. So you just say, I treat these things as equivalent. We of course do that even in elementary logic, right? We all know how to introduce arbitrary names, and we don't usually get stuck. We don't get at the end of the argument and say, well, the arbitrary name I introduced was Alice, so therefore all people's names start with A. Right? We normally don't make that mistake because we know it's an arbitrary name. So in the same way, if we throw something in our models, but we remember we can move it around, we don't usually make a mistake. So I'll give a brief treatment to this because this is interesting technical stuff, but the reason I won't go into super great details because I don't think it will deliver everything we want, although it's a bit of an open. Jim and I worked on this some years ago, and the fact there doesn't exist a paper means we decided it wasn't going the right direction. The long and short of this slide here is, so this picture, this intuitive picture, And here's a model, M, and it sits inside this network of other things. Question is there a way I can be a good logician and talk in a reliable way about what properties phi it has qua element of this network? The answer is yes. It's a little complicated because here's what you should do. You should introduce a theory with two sorts, a sort for objects and a sort for arrows. Category theory. It has function symbols that give you the domain and range of arrows. It has a function symbol that takes each object to its identity arrow. It has composition of arrows, and it's a pretty simple algebraic theory in that setting. Well, what is a model of category theory? It's a category. Boldface C, it has two subsets, it's two sets, C0 objects, C1 arrows. Well, so it has a syntax, and you can come up with formulas in the syntax that have three variables of type object. What things can you say about an object? Well, you can say quite a lot. Again, you can't say directly what's inside the thing because there's no notion of what's inside it, but you can say things like it's a terminal object, which means for every other object, there's a unique arrow from that object to this one. You can say it's an initial object. You can say all sorts of things like that. You can talk about how many arrows there are in and out of it, how many symmetries it has. So you have lots of things like being embeddable in certain other kinds of objects, having a certain number of automorphisms, et cetera. Jim, I've lost track of time. Have I already gone?
No, you have not. We started about 3 minutes late, so you have about 13 minutes until the end of question period.
Okay.
But then we have the discussion afterwards. So.
Okay, I'll hurry it up. Okay. So I don't expect that this will immediately, I've already told you it's not going to work, so I don't expect anyone to think it will. The initial skepticism we might have, the initial skepticism is, but wait, physics also cares about how things look inside the world, right? Physics isn't just concerned with how our world's related to other worlds. And now one might try to get past that worry by saying, in some sense, every feature of everything we used to think about what it looks like inside here can be expressed in terms of how it's related to things outside. The long and short is no, there's not good convincing case that's true. So this may be a helpful thing in understanding some of the features of the models. It certainly helps for those, what I call extrinsic properties, but it's first of all, as a way of representing all the things we care about, it's not very good. And second of all, it's actually in a secret way signature dependent. So here's what I mean is this only gives you properties of a model qua element of a category. So you'd have to tell me what category it's an element of. So that's not just handing you a mathematical object, it's handing you a mathematical object and saying it's of a certain kind. Okay, so I'll quickly whip through this signature dependent accounts because this is well-known stuff. And the end of this story is just that we're going to need more powerful tools. I don't have them myself yet. If somebody cares to try to make this rigorous, that's the direction I think you have to go. Okay, so I said I was going to go with signature dependent properties from conservative to more liberal. So starting with the really conservative case is, so here's a signature, that's just a standard logic thing, right? Function symbols, constants, predicate symbols, relation symbols. First order sentences, of course, yield properties in an obvious way. You just say that the model has the property labeled by the sentence little phi, if and only if the model satisfies that thing. So for example, when does M have two elements? Just in case M satisfies the sentence, there are two things. All the things, or the first list of things I told you, for example, about group theory, those are elementary properties expressible by first order sentences, like has n elements, or n is a finite number. There, of course, are many things you can't say with first order sentences, like has uncountably infinitely many elements. These elementary properties are, of course, as a standard result, they are isomorphism invariant. There are, as I just mentioned, isomorphism invariant properties that aren't expressible by first order sentences. So we know lots of examples of these. So this, unless you're some sort of dogmatic first order person, elementary properties are too restrictive. You have to start going up quantificational hierarchy. All of the standard approaches, and this is how I ran into that Finnish logician's work, is all of these standard approaches, first order quantification, second order quantification, infinitary conjunctions, et cetera, they nonetheless won't tell you about extrinsic properties. So if you want to talk about a mathematical object's relation to other mathematical objects, you either need something from category theory or you need, so Van Nanen's thing is called sort logic, which is actually closer related. So here are my tentative conclusions of this formal investigation. And I hope that these first things certainly are obvious, that there are too many set theoretic properties of models. There are too few category theoretic properties of models. So just these network properties of how models related to other things, there's not enough of those. And so any good account of the properties of models will make these properties signature dependent. Doesn't sound too bad, right? So I'll come back to whether that's bad at the very end. So now let me come back to it very quickly to our examples. And there's much more to be said here that I think is a teamwork project. I myself don't have equipment to do all of the stuff here. It's interesting. So what about relativity theory? And that's actually very current, not only in philosophical circles, so philosophical discussion of what are the features of the model. I mean, in some sense, this is the whole argument. The whole argument boils down to which properties of models do you think are genuine properties? The people who think there's a real whole argument look at two isomorphic or isometric models and they say this one has a property that this one lacks. And other people say no, they have all the properties in common. So they just disagree on the properties. Here, I think actually there's a lot of promise for progress to be made. Lorentzian geometry, it may not be first order in an obvious sense, but there's no doubt, as we saw, for example, in the talks earlier, that when you describe relativistic spacetimes, now I want to be careful about saying linguistically, I mean, it depends where you draw the line between language and math, but insofar as an equation is a piece of language, derivative of such and such equals such and such, Lorentzian geometry has lots of language. But does anyone know exactly what all the bits of a space-time model are that are the features that are invariant under isomorphism? That's a tougher issue. So there's progress to be made on isolating the relevant features of these models. In the quantum case, the situation is much worse than you might think at first. There's a sort of if you take the lesson that notions of isomorphism notions of the properties a model has are going to be signature dependent. And the backside of that is you don't want a notion of properties of models that's not going to respect isomorphism. Now you can change what isomorphisms you have. That's up to you if you want to do it, but you don't want to have both. You don't want to say this is a property of a model, and by the way, it's isomorphic to this that doesn't have that property. Here's an issue in the quantum case that we have to deal with is any two wave functions. Let's block out that word and remember, these are just elements of a vector space. Any two elements of a vector space of length 1 are, not surprisingly, elementary linear algebra related by unitary transformation. It's hard for us to remember when we say, I'm just going to write this down because we say wave functions. This is not going to help me write this down. So, okay, so you think this guy and this guy, those are different, right? Those are different. Those are unitarily equivalent. There's a unitary map that takes the first one to the second one. What does that mean? In the syntax of quantum theory, any property you can ascribe to the first one applies to the second one and vice versa.
Integral under the first one is clearly big.
That's not an isomorphism invariant property.
I'm not sure this is.
It is not. It is not an isomorphism invariant property. So I'll validate your intuition momentarily, because this is what we're doing when we write this is we're picking a basis, right? When I write it like that, I've picked configuration space as my basis. Now, of course, it's true that as configuration space functions, those are not isomorphic, right? So a true wave function realist, if they want to be honest, they'll just say, I don't really believe that the syntax of Hilbert space is the only syntax. We have more predicates and properties. We have those provided by adding in the basis of configuration space. So what they really need is they need an account of the features that are relative to basis. And that's actually, for example, if we write our wave functions, our vectors like this, we're picking this space, configuration space, to be the basis, or at least That's the way we're thinking of it. We're thinking of them as functions from configuration space. I'm happy to talk about this more in question and answer because I'm probably stating things in the wrong way. Okay, good. So let me wrap up. I didn't argue for this point, but I'll just state it again. I think the idea of artifact-free representation is will of the wisp, right? So if you don't know this expression, which I had to look up to remember if I remembered it correctly, right? This idea in old England, right, that sometimes a guy would just get lost in the forest, right? Like your cousin, whatever, he wouldn't come back. And they had this myth apparently where they would see out in the distance like this beautiful shining light, and they would just out in the bogs or whatever, and they would just follow it and disappear. And this is now is a will of the wisp, right? So artifact-free representation is will of the wisp. Please don't chase it. Bother to call your family. So the goal of what I'm suggesting we look at is not at all like the Hartree field, eliminate representational artifacts. I don't think that's possible. But I do think it's possible to make progress on distinguishing the relevant or intended parts of our models from the irrelevant. I think we're always going to have excess there, and that doesn't mean that we can't say, and here's the predicates that I think are the sort of genuine ones. Okay, now this may sound like I share the same opinion that other speakers said that my attitudes towards math first, although I would say if you take it out of context, my attitude toward math first was always really positive if I didn't know what it meant. But after this, I feel even more positively toward it. And so I don't mean to be argumentative here, but I do want to sort of cause us to think a little bit more about it. So the dilemma for language free, or you might say language first, or not quite mathematical first accounts of the features of models, is if models have sets, then they have more properties that physics cares about. And if models are objects in a category, they have fewer than physics cares about. So we actually are in a bit of a bind here. So we don't have an obvious account of what the properties are, an easy one. Believing that M, a model has artifacts, is tantamount, I claim, to rejecting the unqualified statement that M represents the world. And that's what it means to believe something is an artifact. If I take a model, if I give you a map of California and I say, by the way, the fact that I used white paper as opposed to beige paper, it's an artifact. That means I don't believe California is by nature represented on a white map. So I wouldn't hand you a white map then and say, that represents California, full stop in all ways. Exercise no judgment, because everything that I handed to you is part of the representation. So believing that models have artifacts is the same as saying, I don't think things just represent. I think that there needs to be some exercise of judgment. We use these models in general to generate sentences that describe the world. Going back to the von Trazen type thing, models don't say things. Models don't make claims. We make claims. We use models to do that. And so perhaps mathematics first, but not only mathematics. I'll stop there. Thanks.
Okay, I see Dave and Toby. I think that what David meant though, Hans, was that the integral of the squares of those two curves weren't equal.
Yeah, I made a narrow point. It was almost a joke.
Oh, sorry.
Thank you.
Thank you. Okay. Thank you, David. So I was starting to split. I was like, oh no. But I've just been reviewed my drawing skill.
I've been pretty facetious.
Thank you.
Serious.
Yeah, so on the issue of artifacts, right, I take it that the type of concern that folks like Field and Sider have is that one must be very careful when assuming that the things that your theory says that you think are real, that it's a coherent possibility to suppose that those things are real, and the things that your theory says that you don't think are real are not real. Because it's very easy to get into a situation where you have a theory that says the following things, blah, 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 and say, I'm a realist about these ones and not these ones. And then you've said something that's impossible, right? So a nice thing about—
Wait, what's an example of that? That's what, I mean.
So like, for example, it can be, if you take a gauge theory, it's not 100% easy to tell which of the properties of the theory are gauge invariant. And so you say, like, you might say, I'm a realist about this, like take the Hamiltonian GR example, right, to take a very clear one, right? Say, I believe in Hamiltonian GR, and also the precession of the perihelion of Mercury is real. right? Is that,
Yeah, okay,
can you
good,
say
good.
that, right? Like, it's not at all clear that you can say that. So it's like, even Ted will say, yes, there are artifacts, like the color that something is written in is obviously an artifact, of course. But the stuff that the theory says that has a semantic kind of character, we should be very careful about saying that stuff is artifacts and I don't need to say anything more, because if you say that,
Yeah.
then you haven't coherently shown that the things that you think are real, and the things that you think are unreal are also unreal. Those two things could contradict each other.
Okay, good.
It's a subtle way.
I understand this concern, and I would guess sort of historically it traces back to the observable, unobservable distinction thing, right? Where some of Putnam's early criticisms were, right, is you think you have a clear line, but actually what's going to happen is you're going to slide into, ambiguity. Now, the funny thing is also I have to sort out what I think about this, because I'm also against sharp lines in this setting. Like I'm trying my best to get a sense of what actually this magic that physicists do, because I do think it is kind of magic. It's like I think that good physicists, they have this pretty amazing ability to, I mean, mathematicians do this too in their own way. It's an example like John Burgess has pointed out many times with like identity. Mathematicians will say something like, in one breath, they'll say, there's only one group of size 3 with 3 elements. And by the way, that group has two subgroups of size 3. In one sentence, they've said 2 things that obviously contradict each other, and yet it's perfectly fine because they have this ability to context switch that we as meta mathematicians, meta scientists haven't figured out quite yet. So I would suspect the same thing happens in physics. And so my own feeling is, I would say, we all would kind of love to have a sharp line where we're assured that things on this side of the line are representationally significant and things on this side of the line are not. Sider and Field, et cetera, would like to go further and take the things on that side of the line and throw them away so we never make the mistake again, right? It's like get an artifact-free representation, and now you're never going to make the mistake of, I would just say, I think the truth is we're going to have to live, this is going to sound like I'm really joining forces with David here. I'm learning to come to terms with subtleties of physics practice. I think in general, there is going to be a gray area of things we just kind of don't know. Like actually, gauge theory is a great example because like Aharonov bone, right? We might have thought, 50, whatever, more than 50 years ago now, right? Many, many years ago. But you might have been like, good, let's throw away potentials, right? Cut them away. Thank goodness. But that would have been dumb, right? Like we would have really missed a lot of good stuff. So I'm okay with like the gray area of like, these things are obviously not representationally important. These things, let's not throw them away. We don't know.
And I have Toby and then David, and then we're going to shift into a more general group discussion.
I want to make, so I agree with a lot of this, and I want to make a little defense maybe of the isomorphism invariant kind of thing. So your example that really defeats it is this, where you add the conjunction of and the continuum hypothesis. Yeah. And the swings on it being an undecidable sense, because that's what makes it counterintuitive. So it doesn't have to be, it could be Riemann zeta, it could be ABC, it could be anything. If you put a sentence that was decidable there, then it would just be an empty property or a trivial property. So it's all swing on this undecidability. Okay, I'm tempted to just bite the bullet and say that I don't want to talk about properties, but just say, this is a formula that has that's got a free variable where you can put m in and it's true. Yeah. And the reason why I want to do that, I suppose, is there's a kind of a long history in logic of people trying to solve this sort of problem before. Like you think of Kit Fine's work with his duets and stuff. Think of the relevant logic tradition in Pittsburgh in Australia, and even back to Ayer with verificationism, and it's all been an unmitigated disaster. It never works. So I think the right kind of conclusion is just go, maybe not buy into the metaphysics of properties, but just to accept that, this is a sort of pathology. You can go and add sentences to this formulae, and is it a property? Is it really about this thing? I mean, I'm very pessimistic about logic providing the right tool to give you an analysis of aboutness.
Okay.
Yeah. Were you also thinking that the quantifiers would help in this thing? I thought I got a suggestion there with the stronger logic quantifiers might You thought they might help, but I don't know what they want.
Well, no, so that's just, so if you want to keep adding properties,
Yeah.
but only add isomorphism invariant properties. So there are these old results that I don't know very well. I think it was Van McGee or whatever, right? Where it's like every isomorphism invariant property is expressible in like L sub infinity, like some crazy powerful
Yeah, yeah.
logic. And actually somebody, I mentioned this stuff casually, another mathematician said to me, that's the obvious answer. I was like, really? So I don't know, but actually where I stopped thinking so hard about that was when I talked to Juliet Floyd, who's, right? Juliet Kennedy.
Julie Kennedy, yeah.
Okay. And she said, yeah, Yoko has solved that problem. And I looked at it, I was like, oh, yeah, this is going to take me 5 years to understand what it's doing. But it was like, it's a more elegant way of trying to include all of that tower of higher quantification. But then also this additional thing that is kind of mysterious, that mathematicians quite regularly think about the nature of one mathematical object in terms of how it relates to others. And yet they want to do that in a way, or they do that in a way that is trying to be non-sensitive to higher set theoretic things. It is quite puzzling to me as someone who's not deeply into set theory is we'll talk about how things relate to, say, R4. We'll talk about how things relate to the complex unit circle. We'll even talk about how things relate to all vector spaces. But we won't talk about how things relate to higher cardinal number. And it's something funny about mathematics practice. Maybe it's not very systematic. Maybe it's just a practical prohibition on we don't want to be bothered by set theorists stuff.
I mean, I think set theorists want to try and stop you.
Yeah. That may be the answer is to go and tell those mathematicians that they're being bad. No, in a certain way that would validate a lot of what set theorists and meta-mathematicians do is saying, look, it actually does matter. You guys have found systematic ways of cutting off your inquiry prematurely, so to speak. But it would be very natural to ask how, your finite group relates to, this is like Harvey Friedman stuff, right? These all ultimately matter and so on. But actually, I think you're back to your point about aboutness. A delicate thing, I thought for this conference, I could let loose a little bit and Irvine's the one place in the world where you can say philosophy, physics, and foundations of math and let's all talk together. But it's really hard, right? Because the concerns are different. And yet they're both different than philosophy of language and aboutness. But what physicists care about is in some ways skewed to what mathematicians care about. So the properties of models that physicists care about, a logical inquiry is probably going in a quite different direction. Because physicists, I don't know, I'll let them speak for themselves or people who know more about the practice. But the aboutness stuff, my sense is that's not what physicists are concerned about primarily when they're talking about the features of models they care about. It's not quite the philosophy of language issue, but it's certainly, they're not going to wait for logicians to come tell them what the properties of models are that they should care about.
Okay. I thought it was wonderful talk. I'll say some more substantive things for the roundtable. I wanted to say something a bit narrowly about quantum mechanics. I mean, I think I don't want to defend wave function realists, but I do think we shouldn't think that the relevant structure preserving group in quantum mechanics is just the unitaries applied to a bare Hilbert. Any given quantum theory is going to have an observable algebra of some kind, and it's going to be tight. I mean, take an example close to your heart. We think about AQFT.
Yeah.
It's not going to be the case that I just want to say the right structure preserving that is simply a unitary on the state space, leaving the rest of the algebraic structure alone.
Yes, I mean, this is a case where I don't know really how to make sense of the principled way physicists block that. And then there are certainly, so look, we can go somewhat downstream and say certainly you want symmetries that preserve the Hamiltonian or whatever, preserve the dynamics. But even before that, look, it would be ridiculous for me to go to physicists and say, look, position and momentum are totally symmetric, right? There is the Fourier transform after all. So actually you should stop using the word position because it's interchangeable with momentum, right? There's only one thing, position momentum. And actually, by the way, any continuous spectrum observable, I mean, that is true. Any continuous spectrum observable is unitarily equivalent to another. So you think that destroys all of physics practice in a certain sense, is that, look, I will say, but it is a bit, I think the the group that's in the most trouble with this is those who take mathematical formalism and before consulting physics practice, look at purely the structure of the math formalism and try to think what must be the physical story. Because Hilbert space is an extreme case. It's a homogeneous mathematical space. Now it's maybe, I suspect this won't yield fruit. One might say there's sort of a reduced, like not reduced Hilbert space, but there's a sort of reduced space of the relevant symmetries. I'm suspicious that will work in the quantum case because look, I just don't think, I mean, quantum theory is not a gauge theory in its essence.
I think you can get you can say something a bit systematic. You can say something about you want to play nice with space-time structure and you want to play nice with the compositional structure and then how that plays out to particular theory. Like, I think in AQFT, this is actually fairly clean.
Yeah, this could also partly be about the weirdness. Elementary QM is very strange. And obviously a very, in certain ways, broken theory. I don't mean like the measurement problem. I mean, it's like the very fact that you assume that there's these individuals called particles that you can put together and then suddenly they have entanglement, stuff like that. And symmetries are, come from the individual parts and so on. So anyways, thanks for that suggestion. I think it's good. And
Jeff actually had a finger, I think.
This is just a small thing. I know there's going to be a discussion. I just wanted to say once that I really like that quantum mechanics exam because it points out that they're baking in more to our understanding of even the mathematical theory than what's there in the Hilbert space. In this particular case. We're super embarrassed when we have to choose a privileged physical observable. But that's the kind of thing we have to do in order to get traction here. We have to say what it is, we have to specify a basis and then say something about what it means physically. And then we have the traction we need to go. Not that we just have symmetry every direction.
Yeah, so I think, again, this is, I appreciate, I think one thing that is very interesting here, and this is a slight, if one can have an advantage by being ignorant, this is once, so again, if you're used to using this math to do physics, one can be, and this is not me, right? This is somebody else. You can be a little bit blind to how lacking the math is in structure. Like a lot of the structure comes in our use of the math in application and so on. But if you come at it from a more mathematical point of view and you just look at the formalism, you're like, that formalism tells us like almost nothing. How we're supposed to physically interpret that, it's just very opaque.
And we might want it to fall out of the Hamiltonian or something, right?
Yeah.
Have some kind of emergent structure that then gives us a foot in the door for interpretation. But the mathematical model itself just isn't going to do it.
I really want to disagree with this, but I think
I think there's a discussion to be had here. I mean, like I was thinking this whole time, I'm thinking, because it is also true that once you start to think more about the actual physical situation, you go back and you look. I'm all in favor of math first, second, third, fourth, maybe only the odd numbers, right? That comes in. I like the idea, right, that we take math, it's not sufficient. We start thinking physics again, and then we update the math, right? We make that, and this I think was going along the lines of what Dave was suggesting here is, look, in real life, we've got more stuff available like space-time. And once we start, so I'm not, and I think you're not disagreeing with this either, is maybe at any given stage, the math is incomplete in the sense of there's a lot of tacit knowledge about how to use it and so on. But like, it seems like always at the next stage, we can make the math a little bit better so that it's sort of, and I think this is what we do for future generations, so to speak, right? It's like we don't want them to have to rely on, it's like the thing I start with Euler, right? Is you don't want future generations to have to rely on good intuition. You want to say, hey guys, here's how you apply it in this situation. Here's the math. But I think it's a very good open question. I'll let you guys fight it out afterwards about how much right now you can get out of the math.
Great. Well, join me in thanking Hans. And